talk about something that is statically indeterminate. So far, our structures have been constrained such that we've been able to resolve the system using only the equations of static equilibrium. You recall that in most of our problems, which are two-dimensional, there are three equations of static equilibrium: sum of the forces in the x equals 0, sum of the forces in the y equals 0, and sum of the moments being equal to 0. In 3D, that would amount to 6 equations, and here in the simple problem that we have here, which is fundamentally constrained to a single dimension, or the x direction, we have one equation of static equilibrium. The sum of the forces in the x direction is equal to 0. So because this problem is statically determinate, we have enough equations to fully solve the system. If we draw the free body diagram, we remove the support, and we replace it by its reaction force. And using the equation of static equilibrium, we're able to determine that the magnitude of that reaction is equal to P in the other direction, or RA is equal to P. Further, using the method of sections, we can determine what the internal forces are, in this case, between support A and the point of load application. We can see that the internal force is equal to P, or between the point of load application and the support at B, there is 0 internal force. Again, all determinable using the equation of static equilibrium. However, if we increase our constraints, i.e. we add an additional support, the loads are distributed differently through our system, and the equations of static equilibrium are insufficient to fully resolve the system. So, we see a statically indeterminate problem here where we have a support both at A and at B, and again the load P applied somewhere in the middle. We'll use our one equation of static equilibrium for sure, but we'll see that it's not enough to resolve all of our unknowns. Let's draw the free body diagram. Shown here, we see that there are two reactions, a reaction A and a reaction B of some unknown magnitudes, going opposite to the load applied P. So we have two unknowns, RA and RB, but only one equation of static equilibrium. This means that this system is indeterminate. Again, we apply the method of sections, and we can see what the internal forces are. Here between A and the point of load application, we have RA. Here between the point of load application and B, we have P minus RA, or RB, if you will. But we can't determine either of those with what we know right now. To sum this up, the system has one additional unknown. Then we have static equations, and is thus considered statically indeterminate to the first degree. It will require one additional equation to solve it. We're going to get this equation from a look at the system's displacements. The equation itself is referred to as a compatibility equation. So let's think conceptually for a second. Here is our system again, the same system that we looked at before, and we know that that load P is going to distribute itself in the two different directions, some towards the support at A and the reaction at A, and some towards the reaction at B. What is it that will ultimately decide, what physically is it that will ultimately decide the portion of load at each reaction? Let's draw the free body diagram. Here we have RA and RB. Couple things to consider. Where is the load applied? If the load was applied in the center, we would have, and all of the properties of the bar are the same, left and right, we would have a symmetric system. And so we could probably deduce that the reaction at A would be equal to the reaction at B. However, if we were to move that load and it were to get closer to one of the supports or the other, we can probably surmise that the location will affect the way the load paths are distributed. If shown here, we see how when it gets closer to one side or the other, that load or that reaction is a greater proportion of the two reactions. How about the material? If the material was different on one side of the point of load application to the other, would that affect how the load is distributed? Let's say we were to choose a particularly strong material or a stiff material and put it between A and P, and a less stiff or a weaker material, and we were to put it between the load and point B, shown here conceptually, we see that the stiffer material attracts a greater proportion of the load and will have a larger reaction than on the other side. We can also imagine that the cross-section will have a similar effect. Here, where we have a large cross-section of the same material, again, attracting more of the load and making sure that the reaction on that side is larger than the other. So the system that we're going to introduce uses the theory of superposition, which we discussed earlier, to help give us the tools we need to solve this problem. Here we see our system, statically indeterminate because we have reactions at both A and B and only a single equation of static equilibrium. Shown here, sum of the forces in the y is equal to 0. So in order to resolve this system, what we're going to do is we're going to break it up into two independent systems, which when added together equal the final system that you see here. And in that way, we're using the theory of superposition. So we'll start off by establishing a primary structure. The primary structure is established by removing one of the additional supports. In this case, I've removed the additional support at A and kept the support at B. We can then see if the load P is applied, that we will get a reaction at B, but we annotate that with a little subscript 1 to indicate that it is not the same as the reaction of By in the original system. Note that there is no reaction at A because that support has been removed. Because there is no support at A, it is free to displace, and we see that the structure in this case would shrink and go down to the displacement A1. Now let's add our redundant structure. So this is where we put that support back in as an equivalent force. So where it would have generated a reaction at AY in the original system, let's apply that force, that reaction AY, to the structure at point A. It will cause a reaction RBY2 down at the bottom, and overall, because it is in tension, it will cause a displacement A2 at the top. What becomes really important to know, or to remember and to check at every time, is that this is the theory of superposition, which is to say that the redundant structure plus the primary structure has to equal the original system. So if we look across the top, at the top we have RAY in the redundant structure, no reaction in the primary structure, and that equals RAY in the original structure. Looking at the point of load application, we have no load applied to the redundant structure, P applied to the primary structure, and that equals P on the original system. Finally, on the bottom, we have RBY2 on the redundant structure plus RBY1 on the primary structure, and that they have to sum together to equal RBY on the original structure. Now we need to also, now that we know we have our system laid out with a primary structure and a redundant structure, is we have to come up with our compatibility equation. And to do this, we're going to look at the displacements and make sure that the system remains physically compatible. So in this case, we can look at the displacement A1 and know that it has to sum to the displacement A2 to equal the displacements at A. And in this case, because at A it was constrained and not allowed to displace, it also has to equal 0. So we come up with the compatibility equation of delta A is equal to 0, which is equal to the sum of delta A1 and delta A2, shown negative here because they're in two different directions. As we talked about before, we also know that RBY is equal to RBY1 minus RBY2, negative because of the different direction.